So first of all, this one's pretty simple. You get very simple triple bond. This should be the smallest alkyne ever existed because two carbons are needed to make a triple bond, and that will make a two carbon. It's as simple as that. This hydrogen, either hydrogen can be taken away by the base, strong base, like a sodium ion. Then you can add it onto your chain. So that's how we're going to make this. This has a methyl groups here. This has an isobutyl groups here. We can add those two by the SN2 reaction. So what we need to do, first thing is, we take these protons away, make it anion, acetyl ion, or negatively charge it, and that becomes a new profile. So we can decide to put either end. Let's say we treat this in a methyl bromide, then this is just nothing but SN2 reactions. The carbon becomes a new profile after taking the protons away. That attacks the alkyl halide by the SN2 reactions. We just make a carbon-carbon bond. So that way we can introduce one chain. We introduce a methyl first. Still, the next step is there's that proton on the other end of the triple bonds. We can take it away by adding a base, same base, strong base, sodium amide. That will pick up this proton, make this triple bond charge it again, make it recharge it. That becomes a good profile. We need now to change this one with the halogens on it. So that is like isobutyl, bromide, right? Same as in two reactions. These carbon anions going to make an attack here, kicking the bromines out. This is nothing but SN2. Introduce that chain. So it's a series of the reaction. Making a new profile by using a base, strong base, sodium amide. SN2 reaction with the alkyl halide. Taking hydrogens away by the base, and then SN2 reactions, and then you assemble the molecule part by part. Pretty simple. But there are some questions need to be asked. I put the methyl group first. What if we do it the other way? Take this one, and then you make the acetyl ion, same as what we did before, but treat this one first. Can we do that? Which one should we put first? Right? That's the question I'm asking. If you put this isobutyl bromide, the same as a two reaction, we're going to make that. And then this proton will be taken up by the same base, strong base. And then you're going to get the acetyl ion. And then what we need to put, now we need to put the methyl groups. So just a methyl bromide, it'll make an SN2. That happens. Do you see any ones better than the other? Well, in this case, it's actually equivalent. If you put the methyl group first, isobutyl group first, doesn't make any difference. So you can do it either way. So that's totally fine for this molecule. But the issue is the next one. Let's say this is the one that we have to make it. Then how are you going to do it? Let me first give you the wrong answer I see so many times. You see before, the first thing we're going to do, we're going to take, we're going to take hydrogen, we're going to take the proton, and then make an anion, and then we're going to introduce those things as an alkene chain, right? That's a strategy we did. So in order to do that, you use a strong base, take the protons away, and then you get that. And then, methyl groups are not a problem. You can basically do the same way. Methyl bromide, and then SN2 reaction, you can add the methyl groups. Now you need to introduce this part. So let's say we take these protons away again, make an acetyl ion. Now we need an alkyl chains of that. So previously what we did, make an alkyl halide. So treat this. This is the same structure. I only put the bromine here. Make this one, makes an attack, kicks it out, and then you make this. Sounds very reasonable, right? But that's not going to happen. Why? Because of two reasons. Immediate reason I can think of, I can tell you that this is a two alkyl chain, but hydroxyl groups there. It almost looks like a tertiary alkyl. Okay? So it's a very murky. It's a hidden, sacred hidden. The nucleophile SN2 reaction not supposed to happen well with this substrate. That's one type of reason. Very naive. The second reason, which is more hidden, is these reagents is impossible. You're not going to get it. You use this in paper, but you will not be able to get that molecule. Because if you ever made this one, what happened was that these lone pairs of oxygen come in, making a double bond, and you just kick the bromines out, it becomes a ketones. So that reagent only exists on paper. There's no way you can get that reagent made it, and so you cannot use it. Even though you made it, it's aesthetically hindered, so it's not going to be worked. So how are we going to introduce this part? Our regular way using alkyl halide doesn't work. So that means that we cannot make this one at all. So that's the one that I asked you to remember the pattern. Remember that this is a triple bond bonded to the carbon chain, which have an alcohol. How that normally made it? That's made from the carbonyl. If you instead of using this alkyl chain, carbonyl, it's also with electrophile that can be attacked by the nucleophile. So this acetyl makes an attack here. It's going to go up to make an alkoxide. The alkoxide will pick up the proton from the water, then it will just make that. So that's the one you need to remember. And then because of that difficulties using these strategies, we're asking this a lot in the question. So I want you to recognize triple bond, carbon, and the hydroxyl groups. How those things are typically made it? They're made it from the aldehyde, the carbonyls. Now, I hope that I can have a few more minutes. I'm going to talk about switching the order. Remember that the previous example, we can put the one alkyl chain first, and we can add another alkyl chain later, and then we can change the order. It doesn't really matter. Will it be the same in this case? What so far I mean is, let's say we introduce this part first. You put the sodium amide, take the protons away, and then that's going to make a reaction to this, the same reaction we talked about, and then protonation to the alkoxide. We can introduce this one. Then we have talked about then what we can do. We can take these protons away, make another acetyl ion. We need to introduce that by the methyl bromide, right? It sounds perfectly reasonable, because we just introduced the one chain first, other chain later. But that is going to fail. So why that one fail suddenly? So this is the part that you should remember. You know, the base is going to pick up the most acidic hydrogen, right? So what's the most acidic hydrogen in this molecule? This one or that one? That's what you need to remember the acidity. This has a pKa of the 25. That was a pKa of 16. This was a much more acidic than the other one. If you treat the base, you intend to take this one out, but basically you don't go for that. You're going to get this alkoxide prepared, and then when you treat this one's going to get methylated. This is the one you're going to get. Yeah. So what that means is, in this case, order also important. What goes first, what goes later becomes important too. So this question, I really want you to think about. There's so many things that go wrong.